So we were doing determinants, part 9. We did adjoint of a matrix and how to find the adjoint of a matrix. There are some properties, some theorems we discussed already, theory theorem. Now there are some properties of, yes, you note down these properties of adjoint of a matrix, of adjoint of a matrix. First property is A and B are two non-singular matrices of, let A and B be two non-singular matrices of order n. Same order. Then adjoint of a transpose. Adjoint of a transpose of a matrix will be equal to the adjoint of the matrix and then its transpose. Transpose of the adjoint of the matrix. Adjoint of the transpose will be equal to the transpose of the adjoint. Means we can find first transpose and then adjoint, or we can find first adjoint of the matrix and then transpose. The result will be same. Similarly, if you are to find the adjoint and there is some constant with the matrix, then K will come out and it will take the power n minus 1. N is the order and adjoint K is most important. Adjoint K. So there are one mark questions always coming on one of the property of the adjoint. K belongs to real number. Okay. And third property is that I think we have seen adjoint of the product of two matrices is equal to product of their adjoint. Adjoint B, but their order will be changed in like in inverse. A B inverse is equal to B inverse to A. We have seen the property of inverse. A B inverse is equal to B inverse into A inverse. Their sequence will be changed. Similarly, here also adjoint B first and then adjoint A. Adjoint B, then adjoint A. Fourth property is determinant of the adjoint. Adjoint of a matrix, find and its determinant, it will be equal to the determinant of the matrix with the power n minus 1. You find the value and take the power n minus 1. If you are taking 3 by 3, 3 minus 1 is power 2. And if you will find adjoint of the adjoint of the matrix, means first find the adjoint of the matrix A and then again adjoint and then its determinant. Then its value will be equal to the determinant of the matrix to the power n minus 1 whole square 2 times, because here we have taken 2 times, power will be square. And the last property is adjoint of a adjoint of the matrix. Adjoint of a adjoint of the matrix will be equal to determinant of a matrix raised to power n minus 2 into matrix. The answer will be matrix. Here answer is determinant. Adjoint means matrix. Here also we get matrix, right inside matrix. But here it is determinant, here determinant, here determinant. Left side is matrix, so right side will also be matrix. Because matrix cannot be equal to the determinant. Hmm. Got it? Now most important property that is not a property. Now the next topic is inverse of a matrix. How to find the inverse of a matrix. So first we have seen in the matrices that how to find the inverse of the matrix by using the elementary transformation. Now inverse of a matrix we can find out by using determinant inverse of a matrix. That inverse is a square matrix. Property of inverse, you can see first that what is inverse. As you have seen, A is a non zero square matrix. Then if A into B, we have seen actually. So in matrix A into B into A is equal to I. If A is a matrix of order n, then B is called the inverse of A, and this is denoted by B is the inverse of A. B is the inverse of A. That is A inverse. We can say that B is nothing but it is the inverse of A inverse. So we can say that A into A inverse of a matrix with it multiply with the matrix or pre-multiply or post-multiply, and it will be equal to the unit matrix. And second theorem is theorem we can prove also that theorem. So I'll take the theorem here, and theorem is a square matrix A, a square matrix A is invertible. Means inverse exists. If it is invertible, means its inverse exists. If it is invertible, that means its inverse exists if and only if and only if A is non-singular. As I told you before also, non-singular. What is non-singular matrix? Non-singular. This theorem can be proved also, and we get the formula, one important formula from this theorem only. So, let A be an invertible matrix. Invertible matrix of order n. When we are writing order n or m, that shows that it is a square matrix. When it is not a square matrix, we are writing the order m into n, m rows, n column. And let instead of in, we are taking ib. an identity matrix, be an identity matrix be an identity matrix of same order n. So these are two matrices. Then there exists a sign for there exists. In mathematics, there exists a square. This sign means there exists. So there exists a square matrix B of same order n of order n such that AB into BA is equal to unit matrix. Okay. A is invertible, so there must be one matrix which will multiply with A, will give you the unit matrix. Now we take AB is equal to I, and therefore determinant of AB is equal to determinant of matrix I. So the determinant of AB matrix, determinant of the unit matrix equal to 1. Value is 1. Okay. And we have seen determinant can be written as A determinant into B determinant. A into B, determinant of A into B can be equal to determinant of A into determinant of B. And the product of two numbers is 1, which shows that determinant A cannot be equal to 0. Otherwise, if this value is 0, it will become 0. So this shows that A is, hence, after this I am writing here, hence prove that A is non-singular. First of all, A is non-singular. Now we will take the converse of this. Now conversely, uh, let A be non-singular. Conversely, we have taken A invertible, then A is non-singular. Now we will take A be non-singular, then we will prove that it is invertible. A be non-singular. If it is non-singular, then we can say that determinant of A will not be equal to 0. And with the by theorem 1, by theorem we have written that is actually 1. We can write only by theorem. We have A into, we can say into A, adjoint A, or adjoint A into A, adjoint A into A is equal to determinant A into I. This we have proved in the previous question, in the previous class. And A into adjoint A. Okay. Can be written as this determinant we can take left side. This determinant, we can take left side. So it will become into A into adjoint A upon determinant A. And this also adjoint A. Both sides we are taking together. Adjoint A upon determinant A into A will be equal to unit matrix. And this implies that A into B, the another matrix is A into B or B into A is equal to I. That is already there. We have taken. So when you equate this with this one, we get B is equal to where B is equal to adjoint A upon determinant A. In both the cases. Adjoint A upon determinant A is the value of B, and B is what? The inverse. And A is invertible, thus A is invertible because determinant A is not equal to 0 and it is divided by this. So that shows that A is invertible. A is invertible. Okay, so proved A is invertible. But we got the formula, and B is what? B is the A inverse. So now we will find the inverse of a matrix by using this formula. A inverse, if we have to find, we will use the formula A inverse is equal to adjoint. You will find adjoint A divided by determinant A. This is the formula that we will use to find the inverse of a matrix. Before we did inverse by using elementary transformation, now we are using this one. And properties of inverse, then inverse is this one, and properties of inverse we have already seen. Again, see that properties of inverse of a matrix. Inverse of the inverse is a matrix itself. You can write A and B be two invertible matrices. Then you can start properties. Let A and B be two be two square invertible matrix. We can find the inverse of a square matrices only. Invertible matrices of same order. We should have same order of same order, whatever the order is, but it should be same. Then these properties are followed. Number one, inverse of a inverse is a matrix itself. Inverse, and then if you will find again inverse, it will be a matrix A again. Second property is, as I told you, A, B product, inverse of the product is equal to product of their inverses, but in the reverse order. Third property regarding transpose and inverse. If you take the transpose of a matrix and then inverse, it will be taken like first inverse and then transpose. Sometimes it becomes easier. So the question is asked like this, we can do this one. If our question is asked to find inverse, so that depends on the question. fourth inverse determinant of the inverse. Determinant of the inverse. Keep in mind when we are writing determinant means some value, and matrix cannot be expanded. And fifth property is that we have already seen A into A inverse, and A inverse is equal to A inverse into A is equal to unit matrix. And sixth property is if K times you write K times a matrix A and its inverse, then it will become 1 by K, because my inverse power will come on K, 1 by K times A inverse, where K should not be equal to K. So now we can find the inverse by using some, mainly we have the questions where we have to find the inverse, and inverse is equal to, you know that we have seen just now, inverse of a matrix is equal to adjoint A divided by determinant A. And we have seen how to find the adjoint. We will find the adjoint and then we will divide it by determinant. We get the inverse of a matrix. So we are taking one question. Find the inverse of the matrix. 3 by 3. And find, question we are taking, find the inverse of, find the inverse of a matrix 1 minus 1 1, 2 minus 1 0, and 1 0 0. You have to find the inverse. So as we have seen, we have to find the adjoint and determinant. Of course, you can find the determinant. It is up to you to find determinant first or adjoint first. So determinant first, determinant find 1 1 minus 1 1, 2 minus 1 0 1 0 0. We can expand along third column C1, along C1, because 1 0 0. So 1 is positive. We will take this 1. This 1 is deleted from the row and column. What is left? 2 into 0 0, minus minus plus 1 1 the 1. So 1 into 1 1. So you got the value of determinant as 1, which should not be equal to 0. It is compulsory. If it will come 0, we cannot find the inverse. Okay. Now we will find adjoint. We have to find the adjoint of the matrix. For finding adjoint, you know that you have to find the C11. C11 is this number after deleting from this row and column where this exists, and minus 1 raised to power 1 plus 1 2, and we are left with minus 1 0 0 0. So answer will be 0. Now you have to find C12, means this second number, and this is in this row and in this column, so delete this, and minus 1 raised to power 3 negative, and what is left here, 2 0 1 0, 2 0 1 0. So 2 into 0 0, 1 into 0 0, so nothing to do with negative sign because it is 0. C11, C12, C13. Similarly, we will find C13. I told you how to find. Just this row, this column, and minus 1 is to power 4, 2 into 0 0, minus minus minus, 3 times minus, so minus 1. C13. Similarly, we will find C21, 0, C22, you will get minus 1, C23, C23 again minus 1 will come. C31, C31, 1, C32, 2, C33, 1. Okay. Then matrix of cofactor adjoint. We will find the adjoint of A. So what is the adjoint of A? Adjoint is the transpose of this matrix C11, C12, C13, C21, 22, 23, 31, 32, 33, and transpose means first row will become first column, 0, 0, 1 will become first column, 0, 0, minus 1, second row 0, minus 1, minus 1, third 1, 2, 1. So we get the joint and it is divided by the, therefore A inverse is equal to adjoint A divided by determinant A. So determinant generally we used to write like this, determinant A into adjoint A, because determinant is the value and adjoint is a matrix. So determinant is 1, so 1 by 1, and adjoint is a matrix 0, 0, 1, 0, minus 1, 2, minus 1, minus 1, 1. So we got, therefore A inverse is equal to, if here number will come, we will multiply. 1 by 2 will come, we will multiply inside. So we get the inverse 0, 0, 1, 0, minus 1, 2, minus 1, minus 1, and 1.